please welcome Axel.
Thanks, Sydney, for the nice introduction and for having the opportunity to present here. Today I will discuss about the convergence of HPC and deep learning from two different perspectives. So on one side from the system architecture perspective and on the other side from the scientific perspective. So we are seeing more or less three important factors to drive changes in HPC. On one side, we see since a couple of years that we don't get any additional single-thread performance from the processors, so that we have to go more wider, that we have to use more cores, that we have to use parallelism in order to get better performance out of the systems. On the other side, as a second factor, we are seeing more and more cloud-based usage models. So in situ execution workflows which combines interactive simulations, visualizations, data analytics, AI, deep learning, etc. And we are discussing with customers more and with HPC customers more and more service-oriented architectures which are coming more from the enterprise world, but are going into the HPC world as well. And as a third factor, we see more and more data are available coming from experiments, coming from large accelerators, and we need new approaches, AI or data science approaches, in order to use these kind of data to get more insight, better scientific results, etc. So we need more improvements in accuracy, completeness, and response time, especially in order to handle these kind of data amounts. So to underline the last factor, here are some experiments which are coming or upgrading in the next 10 years. So we all know about the LHC at CERN, for instance, which will increase the data volume over the next couple of years by a factor of 10, or the coming SKA project, which will produce 1 exabyte per day in terms of data. So we have a lot of microscopes, so cryo-EM is a very popular approach for handling the microscopy data. And there are a lot of other experiments which are providing this kind of data. So we are developing as NVIDIA a platform which should handle all these kind of requirements for HPC as well as for AI. So one data center platform to handle, to push the developments forward in HPC and AI, deep learning especially. So we have here the Tesla platform stack based on the GPU hardware. So our Tesla GPUs, our own systems, the systems from the OEMs with the GPUs, and we see much more demand on GPUs in the cloud. So most popular here, Amazon, Microsoft, Google, etc., who are providing GPU power to the community. So on the right-hand side, you see here the HPC stack on top of the hardware stack. So the compute works with CUDA, C, C++, Fortran, and also the PGI, OpenACC, directive-based approach, for instance. There are a lot of ecosystem tools from NVIDIA as well as from third party. And at the top, the applications in HPC. So we have more than 500 GPU-accelerated applications meanwhile. And we have a GPU-accelerated application catalog, and you can look into this catalog in order to find application. But with the OpenACC it's much easier to accelerate the GPU, the codes, and to bring it to the GPU because of this directive-based approach. On the left-hand side, on top of the hardware, you have this so-called deep learning SDK. So QDNN, as one of the most important library, provides primitives for developing neural networks. And this is more or less the basis for all the frameworks here, which are very popular in the data analytics deep learning world. So TensorFlow, Theano, PyTorch, MXNet, Caffe, etc. Microsoft Cognitive Toolkit. So more or less all the popular frameworks are accelerated by this QDNN library. On the other side, you have a so-called NICL library, NVIDIA Collective Communication Library. I will come to this also later. We also have an optimization tool, so-called TensorRT for inferencing. So in deep learning, you have on one side the training session in the data center quite often, and on the other side, the inference topic. And TensorRT is an optimization tool for inferencing. So if you have a trained model, you can use the TensorRT more or less pre-compiler in order to get faster inference. I mentioned the frameworks here, and on top of the frameworks, we find the different applications in the internet service area or enterprise applications, or also in HPC when you combine HPC and deep learning workload. Why are the GPUs so popular for HPC and deep learning? So there are several reasons. Quite important is, of course, the compute power, which we are providing with the GPUs, with the latest Tesla Volta 100 chip. We are providing more than 5,000 energy-efficient cores, together with the tensor cores, specialized cores for specialized workloads. I will come to this on the next slide. So nearly 8 teraflops double precision times 2 single precision, and 125 teraflops of these mixed precision with the tensor cores. And of course, for HPC and as well for deep learning, we have a huge requirement on communication and memory bandwidth. So we made a lot of improvements with the integration of HBM, high bandwidth memory. With a Volta GPU, we have 900 gigabytes per second memory bandwidth, and with a stream benchmark, we get around 850 gigabytes per second as usable memory bandwidth. Also, we integrated, starting with the Pascal generation, the so-called NVLINK architecture. So we have a very fast internal communication inside the system between the GPUs. So we have 6 links coming out of each V100. Each link has a bandwidth of 50 gigabytes bidirectional, so 25 gigabytes per second in each direction. And we also further develop this technology, and I will show you one example later in the presentation. I talked about NICL, the NVIDIA Collective Communication Library. More or less, we are using technology which is well known in the HPC world in order to make the collective communication very fast and powerful. So the NCCL can be used also with MPI codes in HPC codes, and also in the deep learning space where all the frameworks are based on. And we heard yesterday about GPU Direct RDMA from Mellanox. It's another technology in order to scale the deep learning training sessions and the HPC jobs beyond the nodes. via the InfiniBand, for instance. So very important features, and more or less these are the important factors why the GPUs are so successful for HPC as well as for deep learning. So we analyzed over the last couple of years what's happening inside the deep learning training sessions, and we found out that some operations are frequently used in order to calculate the weights of the neurons, and we decided to implement these kind of operations in hardware. So we have specialized functional units, the so-called tensor cores, and they are implementing here 4x4 matrix operations, A times B plus C. A and B are half precision matrices, and the accumulation is single precision or a half precision, for instance, for inference. But for training, a single precision, and this gives a good performance for this kind of deep learning, and you can access these kind of operations via the QDNN, cuBLAS, TensorRT libraries, which we are providing. And there's also a C++ CUDA warp level interface in order to use it. So, and I know some HPC customers who are trying to use also the the tensor core performance for HPC codes. So, and you see here in the next slide the performance improvements we can get out of the tensor cores. Here, especially on the right-hand side, you see a comparison between the P100, which doesn't support the tensor core, and the V100 with the tensor cores and the mixed precision operations here. And depending from the metric size, you see a speed up of a factor of nearly 10 for these kind of operations. And we see, especially for deep learning workloads, speed up of a factor of more than 3 in many cases, coming from Pascal to the Volta architecture. I mentioned communication between the GPUs is very important. So we also heard yesterday about data parallel training and model parallel training. Data parallel training, you start the neural network several times on the GPUs with different data batches, and NVLINK allows the separation of data loading and gradient averaging. The same here for model parallel training. So all the workers train on the same batch. You map more or less the different layers of a neural network to different GPUs. And then, of course, you have a lot more of communication bandwidth. So this means you need some features which speed up the communication between the GPUs. And NVLINK is a very good feature for speeding up. So here's a comparison between a PCI Express-based system. So more or less the data loading from the host memory goes via the PCI Express to the GPU memory, and also this kind of gradient averaging goes over the NVLINK, goes over the PCI Express, whereas on the right-hand side with the NVLINK based system, you see the traffic is decoupled. So the data loading from the host memory is going via the PCI Express, and the gradient averaging is going over the NVLINK. So no sharing of communicational resourcing, you have no congestion. And here in this slide you see the performance improvements for some of the training jobs. So you have here a CNTK or ResNet 50 training, and you see here, for instance, for 8 GPUs, you get with a PCI Express-based system around a speed up of around 5.7, and with the NVLink-based system, you get nearly 8, so linear speed up 7.53. So this comes from the separation of the workload. I discussed about the nickel library. So meanwhile, we have the version 2 of the nickel library, and we also support multi-node communication and also automatic topology detection. So this means we are using a ring topology in order to exchange the collectives between the GPUs also in multi-nodes. So we can go over InfiniBand verbs or IP sockets, which is a new feature of the NCCL version 2. And we are using this nickel library in order to accelerate the deep learning frameworks, but you can also use it with MPI code, so it's MPI compatible to use this kind of nickel library. You might have heard about the DJX2 yesterday from Christian. The talk also mentioned this system, which was announced 2 or 3 weeks ago at our GTC conference in San Jose. So NVIDIA DJX1 is a system which supports 16 GPUs inside a system. So GPUs have, meanwhile, 32 gigabyte of this HBM memory. And we have 2 of the GPU boards with each 8 GPUs. We have so-called NV switches. I will explain it on the next slide. We have, in total, 512 gigabyte of HBM fast memory. And we have 8 of these InfiniBand EDR adapters here, so which provides you 1,600 gigabytes per second bidirectional bandwidth. So 2 GPUs are sharing one InfiniBand EDR, a PCI Express switch complex, and also a huge internal NVMe-based storage architecture, so 30 terabytes of NVMe SSD storage, and in addition 10 gigabit and then 25 gigabit per second Ethernet topology. So quite important is the NV switch in this system or in this announcement. Before we had in our DJX1 system hybrid cube mesh topology with the 6 links, and not all the GPUs had the same bandwidth to communicate to other GPUs. So this will change with the NV switch topology. So we have here 18 NVLINK ports at 50 gigabytes per second bidirectional bandwidth. So in total, the switch supports 900 gigabytes per second bidirectional bandwidth. It's a fully connected crossbar system with a Gen 2 management port with some management stuff included, and consists of 2 billion transistors. So this means we can design a system which is fully non-blocked, 16 GPUs with 12 of these NV switches, and have a full bandwidth, non-blocking bandwidth between each GPUs in the communication. And from the memory perspective, NVLink provides an all-to-all high bandwidth peer mapping between the GPUs. So we have 16 times 32 gigabytes independent memory regions, and each GPU can directly access the memory of the other GPU, including atomics are supported. And if NV and the unified memory comes into the play, then we are talking about a single memory view shared by all GPUs. So we have a 512 gigabyte unified memory here. And we also support automatic migration of data between the GPUs and user control of data locality. So that's quite important. You have half a terabyte of HBM memory between the GPUs, and you can handle very large data sets, not only for deep learning, also for the HPC community. It's quite important. And we made some benchmarks comparing two DGX1 systems versus one DGX2 system, and we get around 2 to 3 speed up for the DGX2 system for deep learning as well as for HPC jobs. So another very important feature of the Volta architecture is a multiprocess service, which you can use for MPI jobs as well as for HPC jobs, for MPI jobs as well as for deep learning inference jobs especially. So this means you have here a CUDA multiprocess service, and if you start MPI job with several processes on the node, so the processes will be connected to this CUDA multiprocess service on the host, and then the GPU power will be shared between these kind of processes by a single process, by this MPS process. So we are supporting quality of service. We are supporting much more clients than on the Pascal, 48 in total with the Volta, and we have hardware accelerated this work submission, which improves the performance quite well. So, and especially important is this also for inference, so you can use also the Volta architecture for inferencing, so you get very good speed up for inferencing when you use batching, but it's of course quite difficult to program, and you get reasonable performance without batching and using the MPS process, so that you can use V100 for inference without a lot of programming effort for the batching. So we heard this several times here in the conference. Deep learning is more or less a HPC workload, which means there are some differences, slightly differences. So huge amount of compute power is required, but in HPC we are talking more or less about double precision performance, whereas in deep learning we are talking about single, half, or 8-bit precision, especially here 8-bit precision for the inferencing part. Using inherently parallel algorithms, this is the same for both workloads. HPC needs a little bit less memory per flops than deep learning. HPC is more demanding on network bandwidth than deep learning. Maybe this will change in the future, but at the moment the data scientists like system with as much GPUs as possible inside the system. So the 16 GPUs with a DGX2 is a very good fit for them. But we see with new tools like Horwood from UVA that we are talking more and more about distributed training frameworks, and DK Panda also presented some of the tools in order to go much faster into this distributed training phase. What we see quite often is that the deep learning environments, that the frameworks are very complex and time-consuming to build, test, and maintain. So there are a lot of dependencies from library versions, from operating system versions, etc. So that's the same or very similar in HPC, so that we decided to containerize these kind of deep learning frameworks, and also containerized HPC applications. So we have a so-called NVIDIA GPU Cloud Registry in the web, so you can register here at ngc.nvidia.com, and this is a repository for containers with deep learning frameworks, with GPU-optimized frameworks using QDNN, using Nickel library, etc. So you find containers for these very popular frameworks here, TensorFlow, for instance, PyTorch, etc. But you also will find HPC containers, for instance, for GROMACs, GAMAs, NMD lamps, etc. So you can log in, you can download the containers, and you can use it on your system. And this service is for free, so you only have to register here at this site and can then download the containers. And last but not least, not only deep learning or HPC containers, we are also providing visualization containers. So for instance, ParaView with optics, index, and holodeck, as well as index and VMD containers. You can download and can use it. So a lot of effort we spend on this, but we believe that it's worth, because the maintenance of the containers is, or the building of the frameworks is very difficult and time consuming. So we are also using our own technology in-house, of course, hardware and software technology. So we built the so-called SATURN 5 cluster, 660 DJX systems with the Volta GPUs, so 40 petaflops of double precision performance, 660 petaflop of deep learning tensor core performance. And we are using this for deep learning, especially for automotive, but also for other use cases. Also, HPC workload is running on the system, and we made a lot of experience in order to design such a system for deep learning, and we could use our HPC experience to design it. The important point here is that all the workload is containerized. So a user who wants to access the SATURN 5 system has to use a container in deep learning as well as in HPC. So that's a new approach, and we have a very good experience with them. We also published a white paper about data center reference design, especially for deep learning. So it's based on our SATURN 5 experience with DGX1 compute ports and combining the whole cluster together with the InfiniBand, with the storage, etc. So please have a look at this white paper here, at this URL, and you will find a lot of very useful information. So this was more from the IT point of view. Last but not least, some examples about the combination of HPC and AI. So on one side, we have proven algorithms based on first principle theory, so algorithms which were developed 40 years ago and which are proven. We have statistical models in HPC. On the other side, we have new methods to improve the accuracy, insights, and so on with the AI, so we can combine it in a very nice way. So, for instance, we have a lot of projects where customers want to use HPC simulations in order to create data sets for deep learning frameworks. And if you have the trained networks, for instance, you can implement inference models and have a real-time response time, which is very useful. So you don't have to restart a simulation. You can use this trained model in order to get real-time interactivity. So there are a lot of additional things here. Two examples. Here, multi-messenger astrophysics. People are using data produced by the Cactus toolkit in order to train their deep neural network, in order to produce training data, and they get very good results out of this neural network. And here's another AI quantum physics, quantum chemistry example, where also deep learning neural networks will be used for drug discovery. So in summary, we can say that the same GPU technology which enabled powerful science is also enabling the revolution of deep learning. So deep learning is enabling many usages in science, for instance, image recognition, classification, etc. And application can use DL to train neural networks with already simulated data, and DL networks can predict about the output in real time. And last but not least, so GPU is the right technology for HPC and DL. You can use one GPU platform for multiple approaches for HPC, for AI training, for AI inference, as well as for simulation, visualization and virtualization, etc. That's all from my side. Thanks for the opportunity to speak here, and I'm open for questions.